to talk about several things. I'll try to compress my usual hour-and-a-half talk into 30 minutes, too. I'm going to talk about two kind of overarching things. One is that, first of all, I work at the Argonne National Lab. I'm part of the Department of Energy's collection of national labs, and I work in high-performance computing and AI applied to various problems in science. In fact, right now, most of my group is working on coronavirus. I'll be flying back shortly and helping them. But we just put out a report on AI for science, the opportunity for transforming scientific research using large-scale AI. And we're just in the process of fielding exascale computers, and you might have heard of some of that. What I'm going to do for the next couple of minutes, though, is give you kind of a fast-forward view of the future on the next 5 slides. And this, there's a lot of text on here, but I'm just going to kind of act this out for you. So there's 2 big machines that are rolling in 2021. One at my lab, and the machine is called Aurora. One is at the Oak Ridge lab, called Frontier. These will be the world's fastest single integrated computers in the 21 timeframe. And they're exascale class machines. But 5 years from now, kind of middle of the decade, of course, these machines will be running fine. They'll be supporting lots of applications, mixing between simulation, data analysis, and AI, and probably leaning much more towards the AI in this time frame. At the same time, we're going to see a lot of progress in integrating machine learning into changing how we do computations in materials design or designing organisms or drugs, and changing manufacturing. In this time, 5 years from now, there'll be US national initiatives in AI and quantum computing. These will be up and running. Later this year, you'll hear announcements about new quantum computing research centers across the country. There'll be broad progress on applications of AI in science, particularly in the biomedical. So biomedical is things people have raised this a minute ago, but it's an area where there's the community thinks is probably the most fertile for application of AI in the short term, right? There will be additional quantum test beds. Quantum computing is moving, neuromorphic computing is moving, but they're still not useful in some sense, right? We're not building them into the infrastructure yet. There will be devices stood up in clouds that lots of people have access to, and so on. Even in this 5-year window, there'll still be kind of more experimental things. And there'll be progress on software stacks, in particular software stacks that attempt to integrate quantum and classical computing. That's where software stacks are going to go, at least in the space that actually supports quantum computing. If you look out 10 years, okay, so 2030, right, we have a roadmap that we're working on with the Department of Energy to have 2 generations of machines between now and then. So by 2030, we'll be having systems we think that are probably going to be in the kind of 100 exaflops scale, and for things like AI operations, low precision operations, they will be kind of zeta scale machines or beyond. These kinds of machines will start to become radical hybrids. I mean, we will have normal CPUs, some evolution of GPUs in them, and some kind of AI accelerators, and we may have other devices in them depending on whether or not those devices start to mature. And we think that most of simulations in this time frame are going to be managed by AI. So there's going to be another kind of big layer in the software stack where AI is going to get in there. I'll talk about that a little bit later. We will be, in that time frame, trying to design zeta op machines. But these will be very hybrid-like. They won't look like current machines, and we won't really talk about them in the same way. Those of you who know, there's some inside jokes in here about things like LinPack-Q, but I'll skip that if you're not linear algebra people. AI is going to be used kind of across the board for managing systems, for optimizing systems, for optimizing code, for translating code. And there'll be some progress in integrating classical machine learning with symbolic computing. That's a thing that, and I'll even talk about that a little bit later. In this time frame, maybe quantum computers will reach 1 million qubits, and they'll start to be quite useful for simulation type problems. They won't yet be, I think, in this time frame, that useful for solving more theoretical problems where things like Grover's algorithm and so on, Shor's algorithm actually show they would be dominant for discrete math problems, but for simulations for sure. And there'll be groups attempting to extend programming languages to support quantum, right? And we like to make a joke that Python 4, if you're a Python person, you'll know that there's a lot of history over getting rid of Python 2 and moving to Python 3, that Python 4 will probably be quantum enabled, and Julia and so forth, and there'll still be Fortran, except it'll be Fortran Q. But one thing that we're starting to see is that a lot of the actual code generation for quantum machines will be generated by machine learning. So gate sequence optimization and so on will be done by that. And then finally, if we go 15 years out, I like to show this SpaceX landing on Mars, because even though Elon talks about this happening in 24, it actually won't happen until 2035, maybe, if ever. But by then, he's successfully landed. One team that has no way to get back. Gosh, you guys aren't getting any of these jokes. So by this time frame, Zeta Ops, we think will be possible, right? By then, storage systems will behave very differently. Storage systems are essentially going to be front-ended by machine learning methods that learn the distributions of data and aren't just passively storing bits. So any device that actually can store something can also do computing on it, right? So rather than writing your bits out to a memory, you're going to write your bits out to a memory that's front-ended by some kind of a machine learning system on it that will learn the distribution of the data, be able to give you back maybe the real data or give you back fake data that's in the same distribution and so on, meets various concerns. So storage systems are going to be essentially replaced by in situ AI that has all kinds of abstractions for dealing with your data. Nearly everything that collects data will have some intelligence layered on it, and you're able to access it. So all this stuff that Paul talked about, I totally think will happen, and it will be even much faster than that, but there will be various layers of intelligence on it. By this time frame, quantum computers that use distributed entanglement, in terms of networks, should be fairly possible. I mean, if the scaling to qubits follows anything like what had happened with transistors, will be well on that way. And a major use in this time frame, say 15 years from now, for simulation is actually going to be for building training sets for pushing into the tails of the distributions for AI. So anyway, so if we zoom back to today, right, what's happened over the last 10 years, right? So in why we're all talking about AI now is that basically three things have driven progress. One is that we had on the shelf a large collection of pretty good algorithms, pretty good methods, right, that were developed during the 90s, during the 2000s. They worked, they weren't very scalable, we didn't have enough data to really make them break out, but they were on the shelf. So convolutional neural networks have been around for a long time, for example. Second thing that happened is it became quite easy, starting around 2010, to start creating very large data sets. And so things like ImageNet that was started kind of 2006, 2007 timeframe, started coming out. It can kind of be good enough that you could use it actually to drive large training exercises and in competitions. And finally, computing at a high enough performance level became affordable, particularly through things like GPUs. So these are the three things that have made recent progress in AI. And if you were looking at an AI story 10, 15 years ago, it wouldn't look like this. You'd have these things on the left, which are just kind of academic subdivisions of AI. But the thing on the right would just say AI. And it was a collection of about 20 different domains that all had their own specialties. People worked in computer vision, did handcrafted feature recognition. People that worked on language systems built parsers and entity recognizers. And there was no cross-coupling between these things at all. But what's changed in the last 10 years is that because of the compute and the power of deep neural networks, particularly convolutional networks and other things derived from that, and more recently things like transformer, that machine learning is now the unification across almost all of the methodologies in AI. And that's what's changed. That's what has given AI kind of a big boost and has transformed, really, the discipline. A couple of years ago, Andrew Ng wrote a nice article. It was in the Harvard Business Review that just tried to summarize for business people what AI can do. And I mean, you can read some of these examples, like, can you recognize a face, yes or no, right? Is a loan going to get repaid, yes or no? These are things that are, humans are pretty good at this. I mean, language translation, if you're bilingual, right, you usually, and if you're, fluent in both languages, and if someone's talking in one language, you're not really having to think all that hard to translate phrases, for example. So AI today is pretty good at doing these kinds of things, these kinds of tasks. And the kind of meta thing that gives you a sense as to what other kinds of things might a machine learning system be able to do today without being very technical on the analysis of it is, can you do it in about 1 second of thought, right? So, and if you can do it in 1 second of thought, which is almost like no thinking at all, right? You recognize a face without really thinking about it, right? You recognize handwriting without thinking about it. You get in a car, there's a stop sign, you stop, you don't really think about it, right? Those things, if you can do it in about 1 second, we can probably get a machine to do it now and do it more accurately, more consistently than you can. And I tell a joke about teaching my daughters to drive, which is driving is really just 1 second after another not crashing, right? That's the trick, right? So if an AI can drive a car because basically it can drive for 1 second without crashing. Now, having it do a really complex layout of what order it needs to do the errands and visit grandma and so forth while you're actually driving without crashing, that an AI can't do yet, right? So there's been a lot of accomplishments in the kind of what I call in the real world, in the regular world, not in our academic kind of scientific world, but in the internet, big five internet company side of the world. So we have near human level image recognition, image classification, speech recognition, handwriting, right, translation. Everybody's got digital assistants running around their houses, and near human level autonomous driving, and we're getting close to that. And if you start getting down to the bottom here, there's some interesting things. So, AI is doing the ad targeting. So if you're on Facebook or Google or some equivalent in China, the placement of the ads, the correlation of your behavior with what you're likely to click on, that's being done by some kind of machine learning system currently. And of course, a couple years ago, DeepMind pushed out AlphaGo and then AlphaGo Zero that became the best Go playing systems in the world and so on. And what we're starting to see is this technology now translating into the scientific and technical domains. So at the very bottom of this, I say human plus level of image analysis for cancers and other disease diagnosis. So I work a lot in cancer. And right now, if you have a tumor and you get an image, if you get a biopsy and then you have histology, a histologist look at that image, you essentially would prefer to have a histologist with a computer-aided classification system to help you because they're going to be more accurate on average than the average pathologist. Or if you have a breast x-ray and you have it analyzed, again, the computer is going to be, on average, more consistent at finding the tumor than the human pathologist. One thing that happened 2 years ago is that Google's DeepMind, the London subsidiary, the startup that they bought in 2014 or so for about, I don't know, a lot of money, solved the protein folding problem, or at least solved a version of the protein folding problem that happens every 2 years at the competitive assessment for structure prediction. So with this contest, what would happen is the experimentalists that solve protein structures day in and day out over the year would put in a special, hidden place a set of solutions, and they would give the contestants essentially the protein sequence and ask them to predict the structure, the 3D structure. And for a long time, the reigning champion of that was David Baker's group up at the University of Washington up in Seattle, who was a big user of our supercomputers, who had a kind of a hybrid algorithm that did optimization. It wasn't really machine learning, but it was kind of a hybrid folding biophysics algorithm. But in 2018, DeepMind essentially crushed the competition here with a deep learning formulation of this problem. But then everybody got pissed off at them. And they got pissed off at them because they didn't make their code open, right? And this kind of sent a warning shot kind of across the community that groups that have access to massive amounts of computing, like Google and Amazon and Facebook and Microsoft, right, have, in some sense, way more capability to build these systems than everybody else. And if they do build a system like the DeepMind protein folder, they have an obligation to kind of make that stuff available. Otherwise, the academic community is kind of behind. Now, what happened is the academic community actually worked really hard to catch up and now has open source versions, and then eventually DeepMind released their models. But that's a tension that's actually happening that we have to worry about. So what's possible? If we look out, we kind of crystal ball a little bit, where do we think this is going? So I'm talking about high performance computing, largest supercomputers, science, advances in AI, advances in hardware architecture, software, and so on. Well, if you look at what's happening in the general space, using language models, Alibaba and Microsoft were able to essentially achieve a score on the Stanford reading test that was greater than the average human taking that test. And that test is essentially composed of 500 Wikipedia articles and 10,000 questions on those articles. Okay? So this is a typical kind of test that, say, an incoming college student would take, or maybe a high school student would take to figure out how good are they at reading comprehension. So the deep learning language models can now pass that test, and that's pretty amazing. And then last year, a similar kind of test was happening. Similar kind of contest was happening in New York. So New York State has a set of standardized science exams. Okay, they give them. All of our states do this. All the countries typically do this, right? So one like in 8th grade and one in 12th grade, kind of science achievement tests. And 4 years ago, there was a competition where the language AI people were gathered, and they entered a competition to see if they could pass these tests with their language models. And all of them failed. Failed by meaning they got less than 60% or something on the test. Last year, for the first time, an AI system, a language model system based from the Allen Institute up in Seattle, entered this test and got an A on the 8th grade test and a C on the 12th grade test in science. So these, again, are science questions. They're not just reading comprehension. They're actually asking questions about chemistry, physics, biology, and so on. So this is amazing progress in 4 years, going from failing the test to getting an A and a C, and maybe another 4 years they'll get an A on the 12th grade test and maybe get a C on the science component of the ACT or something. But there's been enormous progress happening in language models. In particular, there's been progress in a way that we didn't even think was possible. So this is from a paper from earlier this year from guys at Facebook in the AI research group there. And they took this language model concept. It's essentially the idea of what's called a sequence-to-sequence translator. This is the underlying basis for AI-based language translation. So you got a string in one language, English, and you're going to translate it into Mandarin, for example. And you view that as a sequence-to-sequence translation problem. They took that concept and applied it to solving integration equations, basically integrating math. And this hadn't been done before. And to do this, they used a bunch of computer algebra systems to generate the training data by differentiating formulas. So you generate a whole bunch of equations, you differentiate them. Okay, so the integration operation would essentially be running that backwards. So they generated millions and millions of examples. They then trained their system on these millions of examples and then ran it forward. And it was able not only to do it, it was actually able to work, it was actually able to solve problems in this forward direction that the underlying system that generated the examples could not solve. So it demonstrated for the first time this kind of generalization in this particular problem. But what's interesting about this is using machine learning methods to solve discrete problems we formerly would have used symbolic computing methods to do. So this is a beginning of the integration of discrete methods and machine learning methods. Not to be outdone in some sense, there's a group at Edinburgh who did something that's even kind of weirder in some sense. So how many people know what the three-body problem is? Not the Chinese science fiction story, but the actual math problem. Okay, so if you have you know we have a two-body problem. How many people have heard of the two-body problem? How many people have heard of orbits? Okay, all right. So the moon and the Earth is a two-body problem, right? It's three if you include the sun, but it's a two-body problem if you just include those two, right? And if you're in a universe where those are the only two entities, you can solve that analytically, right? You get an ellipse. But if you start adding three or more bodies in, you can't solve these systems analytically. Okay, they're fundamentally chaotic. So what do we do when we're planning orbits for spacecraft and so on? Well, we have these software programs that do very detailed integrations and try to accommodate all of these effects by all the different bodies. And sometimes these systems will actually get stuck. They can't actually converge. So what these guys did is they took a ton of examples from the numerically solved three-body problem. And some of these are really beautiful in terms of the trajectories they make and so forth. And they trained a neural network on that data and then started asking it new configurations that it had never seen before. And it was able, in many cases, to not only find the new configuration, but do it 100 million times faster than the classical method. 100 million times faster. Not like 10 times faster. 100 million times faster, right? 100 million times faster is very fast. It's faster than the amount of improvement we've gotten from Moore's law, right, over decades, okay? So this idea that by replacing a traditional numerical algorithm with a deep learning system can not only solve the problem, but solve it much faster is out there. That's an idea, and I'll talk more about that in a second. So what are we doing in science now with AI? Well, these are the three, I would say, kind of main things, meat and potatoes things, if you want to think of it that way, baseline things that we're doing. So the first one is that we learn predictive models from data where we don't have some underlying theory. Somebody said, oh, AI is going to be really effective in medicine or biology. And the reason why it's so effective there is because we have no theory, no good theory in biology. We have a little bit of theory. We have evolution, and we have a little bit of mechanistic theory in biology, but we don't have any kind of systems biology theory. I don't have a theory that tells me if I have a tumor and I have this drug, whether this tumor is going to respond to this drug. I can only learn that essentially by huge amounts of training data and building, say, a model for it. So we can do this now, and we can do it quite well in many systems. In examples of predicting materials properties, designing a photovoltaic or designing some new alloy or something. In chemistry, predicting properties of drugs, we can do it in a way that's vastly better than any other method. So that part is working. We can learn approximate solutions to inverse problems. So an inverse problem is one where I have some system. I mean, here's an example. I mean, this is not a simple one, but let's say I have a material that I want to make. So I have some elements, I put them together, I bake it, slice it, dice it, whatever, and I'll have this material that pops out. This material does something. Maybe it's, captures photons and turns them to electrons, or maybe it fluoresces under a certain energy level or something. So an inverse problem would be if to have some material that has that property, what is the starting point? Okay, what's the starting point I need to have? So it's basically running the problem backwards. So this is a fundamental design challenge. Many design problems are formulated as inverse problems. When we do, people have heard of like seismic exploration, where you blow off explosives and bounce sound waves through the earth, and then you listen with microphones and try to recover the structure underneath the ground, maybe for oil or for water or something like that. Recovery of the structure from those sound waves is an inverse problem. So it turns out inverse problems AI can solve in approximate fashion in ways where we actually don't have a good forward model, don't have a good mathematical forward model. So again, if you have enough data, you can train it and it can solve these inverse problems. And finally, we can use these things to generate large collections of synthetic data. So if you take a model and train it on a large collection of data, this could be faces, for example, and if it's a right kind of model, I can go in after I've trained it and sample that model and pull out faces. This is how fake faces are generated, or how fake news is generated, okay? But we can use it for problems like that where we're not trying to make fake tweets for the president or something. We're trying to actually make fake universes, right? So we run forward simulations, say cosmological simulations. We sample those simulations, we train the model, and then we ask the model, give me a universe, give me another universe, right? and we ask it to give us universes that we can then test for things like the cosmological constant. And in that way, we can try to understand statistically what's in the data that we might measure from telescopes to actually give us insights into those parameters. So at places like Argonne National Lab, ones here at Berkeley, at Stanford, all the national labs, have hundreds and hundreds of these kinds of projects going on, where we're applying machine learning to a wide range of science problems. Like again, in cosmology, we're trying to find gravitational lensing objects in the data, things that bend light, for example, or we're trying to use them to analyze the output of climate models to track hurricanes and to count the frequency of hurricanes as the climate warms up, for example. But many, many applications, right? Hundreds of them. But that's not enough. What we want to do in the future, and this is why I showed that slide on the math integration, is that we want to develop methods that can both learn from data and from theory, right? So I don't know how many, I don't know the backgrounds of people in here, but you know, when you're a student and you have a textbook, your professor expects you to read the textbook and be able to solve questions in the textbook, right? But with the current AI systems that we have, if we're trying to, say, solve a problem in quantum mechanics, there's no way I can feed the AI the textbook on quantum mechanics. All I can do is feed them examples. So it's like every time I want to train the system to do some new problem, I have to just come up with examples. I can't give it like, here's the theory, right? So what we want to do in this first bullet is we want to build new systems that actually combine learning on data from learning on symbolic knowledge that might be in textbooks or might be in proofs in math papers, for example. So that we can leverage all the stuff that we've actually accumulated over the last 400 or 500 years in mathematics, which right now the AI systems are completely ignorant of. It's like, imagine every problem, every student you have knows absolutely nothing except for the data sets you give them, right? That's like the current state of AI right now. There's no way for us to aggregate symbolic information as a baseline. So that's one. The second one is we want to automate and accelerate experimental discovery from the idea all the way through running the experiment to collecting the data to planning the next experiment. So this idea of what we call self-driving labs. So everybody has the idea in their head of a self-driving car. It's kind of, maybe it's good, maybe it's bad, depending on whether you're an Uber driver maybe. But you know what it is, right? And if it worked perfectly, you would say that would probably be a good thing, right? This idea of a self-driving lab is you want to find a new drug candidate for a disease, or you want to find, again, some new material that's interesting, or you want to solve some, you want to design an organism that can make some new product, some really cheaply or something. Instead of searching through millions or billions of possibilities, you want to have the AI-driven lab do that in an intelligent way, and that's when we're making progress on. And finally, we want to use AI for actually helping us patch up our problematic theories, like the standard model of physics. So what we've been working on for the last couple of years is a thing we call the AI for Science initiative. Some of you might have heard about this. So last year, the White House put out an executive order on AI, saying it's the #1 research priority for all the US agencies, and for them to prioritize their budgets appropriately. And then in the spring, they put out this research and development strategic plan that is actually giving us a framework in which to do some of this stuff. Last summer, myself, Kathy Yellick from Berkeley here, and Jeff Nichols from Oak Ridge started organizing town hall meetings, getting the community, our scientific community, energized around this idea of AI for science. And this was me on the stage up there in July, kicking off a meeting at Argonne. We just put out this report, so if you Google for AI for Science, you should find this report. If not, it'll be more findable in a couple of weeks when we get it in the right place. But so we have this report that we just published last week that is about 220 pages. It lays out across 16 different domains the opportunities for AI in scientific fields, from materials, chemistry, biology, cosmology, and so on. But also what we have to do in math and foundations, improve data life cycles, software infrastructure, and so on. And it's really laying out not quite a blueprint for this. We had over 1,000 people involved in these workshops over the last year. And it's laying out kind of an overall architecture for how to do it. So we're envisioning a program, about a 10-year program. So it gets me to that second slide of my first two future vision slides, that will focus on building new AI applications across science domains, a new generation of learning system software that will allow us to support the thousands and thousands of researchers that need to be able to build models and do inference on models on a daily basis. Fundamental investments in what we call foundations research. One of the key concepts when you're applying AI to something like medicine or science is that you want the models to have not only the ability to make a prediction, but to also be able to articulate the confidence in that prediction, for example. So that's a fundamental thing that most cat video-based AI systems don't do, actually. And then new hardware for advancing things. So, there's many things that will happen in 10 years. I've already kind of talked about this. One of the things that's really clear is to make progress in deep learning, we're going to need a massive amount of computing. This is why the cloud people are so happy about the advances of AI, because it's going to sell them a lot more clouds. For example, training the AlphaGo Zero system, that's the world's best Go player, took many exaflop days worth of computing, $34 million worth of computing, which is why I mentioned this have and have-nots in the AI research. I mentioned the Exascale system. This is what our system, cartoon of our system that's coming at the end of next year. This will be many, many times faster than exaflops for AI and exaflops for high-performance computing. We're also working with AI startups. So one of the more interesting ones that we're collaborating with is called Cerebus. They're based out in the Bay Area. And they've built the world's largest chip. This is 1.2 trillion transistors. So a wafer about this big. It has about 500,000 processor cores on it. And is hundreds of times faster for solving these AI problems than existing GPUs. There's lots of reasons for driving high-performance computing and AI together. Again, in the interest of time, I'll just skip through this. But I mentioned already the surrogate models that is using AI models to make simulations go faster. We're seeing huge progress in that area. For example, in molecular modeling here, this is density functional theory modeling for modeling electronic structures. If you replace the core algorithm with a convolutional neural network and train it on many configurations, when you go to actually run it on benchmark problems, you get 1,000 times speed up. The reason this is important, okay, is that if you're from a place that doesn't have an exascale machine, maybe you don't even have a petascale machine, but you have access to a handful of GPUs. Those are kind of terascale machines, right? If you do this kind of method, your science is now 1,000 times faster. So this will be a great equalizer across many countries, many areas. We can even use it in searching for drugs. I don't think the video is going to go here, but there's a little pocket here, and rather than using conventional drug, I don't know if you can click on the video there, if you're in the back there. There's a little, so rather than normally how you would solve a docking problem, where you're solving this problem as a molecular mechanics simulation, where you're essentially solving for all the forces, we've been able to do this problem with reinforcement learning. And it is 1,000 times faster. And in fact, this is one of the algorithms that we're using right now looking for antiviral drugs against the coronavirus using this kind of method. And we're envisioning how this might actually roll out as a service. So if you want somebody who's trying to design materials, they want all these kind of special things here. And behind the scenes, you would have modules that are laying out, for example, one that knows how to do a design, that you ask it for properties that you want, it tells you what to make. The next one tells you how to make it. And then if you say go, it goes and makes it in the automated lab. And the third one is one that actually is able to ingest the data, the science literature, and so on. And when you get some new result, that system can actually tell you, what it means, give you some insight. And behind that would be a set of building blocks of AI components that are actually domain agnostic. So design is not design in materials or design in chemistry, but it's a design engine that actually learns across many domains. And so this is my last slide here. So all of this is going to impact society. We think that we can accelerate discovery rates across many areas of science. And in design, get much faster design optimization. We think we can move from simple automation that happens now in labs, simple robotics, towards what we call goal-directed systems or self-driving labs, where it's like a very smart postdoc. You hand them a problem and they go with it. They come back, a week and tell you if they've been able to do it. Simulations are going to become simulation AI hybrids. We're already starting to see this happen at an incredibly accelerated pace. This means that future architectures are going to have more hardware capability for supporting AI-type operations embedded in them in various ways. And software will have to change. The role of software will change. We see the need to build accessible and integrated knowledge bases for scientific information that are queryable with modern AI, much better than just simple keyword searches. And it's going to transform infrastructure. So with that, I thank you. Sorry for going a little bit long, but.
Rick Stevens.
Thank you.
And again, you can ask your question, anything you'd like to know about the future of computing. What would you like to know?
I can make up stories about other kinds of futures too, if you want.
Other futures, oh.
Yeah.
Any preference?
No.
No, okay. Yeah. Who are you and what would you like to know?
My name is Dr. Ala Hagadi. I'm from University of Imam Abdurrahman University in Saudi Arabia.
Yeah.
My question is, now for the AI, is it in future is going to be applied on quantum computers, or it's already using them just for the first operation in quantum computing? But what about the memory? Quantum computing?
Yeah, so right now, quantum computers are not useful, for AI, because AI, in the way that we currently do everything, it's very data intensive, data training. And a quantum computer, to load the data, is a linear operation to build a quantum superposition of the data you would have to train it on. So you would spend all of your time loading the data. And they're actually quite small. Even a 100-qubit machine isn't, the noisy intermediate state quantum machines that we have now are not suitable for this, right? In some future world, right, if we can get to machines that have some kind of quantum memory where I can spend a lot of time loading the data, and then I can maintain those superpositions over some period of time. And I had a big enough machine that is reliable enough that I could apply some reasonable number of gate transitions to it. We might be able to do something. But my prediction is that quantum computers won't impact AI for at least 10 years. I don't see that happening.
So you talked about that analogy with the textbooks and sort of like the idea that with supervised machine learning, you're constantly like feeding in examples to your model, but it's not really the entire entire universe of potential data. So where do you see unsupervised machine learning?
Well, so unsupervised learning doesn't fix that problem. It's just right. So that just means I have lots of data that's not labeled, right? And there's all kinds of methods for gaining value out of unlabeled data. Learning clusters, learning the structure of that data, and learning the distribution of that data. If I have some subset of this labeled, I can do semi-supervised stuff and project labels, right? There are methods. One of the great things that's been happening in language processing is the idea of self-labeling. So if you look at, there's tons of papers on this, but if you look at how modern language models work, they don't use labeled data. They have big corpus of text. They go in and do a couple of simple ways to build training sets. So one thing they go in is they essentially mask out words. So they just block out words, and the network is trained on everything, and then it's presented these examples with words masked out, and it has to predict what's there, and so it learns how to do that well. Okay, so that's a way to get kind of sentence comprehension, and then to get more kind of sequential comprehension. When you read something, it's pretty easy for us to understand the antecedent to an argument. So we read something kind of linearly, and we say, okay, this happened first, and this happened second. And if someone later asks you what part of the story, they just read you a sentence back, read you, say, 2 sentences, you can pretty accurately say, well, this one had to have come before this one, right? So you can do that same kind of self-labeling in text data. So you just number the sentences, essentially. And again, you train the model on a pile of stuff, and then you hand it additional things and have it predict which sentence is first or last. So these are really self-labeled data, right? It's unlabeled in the sense we don't have classical labels, but you can derive a label from it. So there needs to be a bunch of work in that kind of space.
Yeah. Final question.
Given the impending rise of quantum computing,
Yeah.
what sort of applications do you foresee being on quantum computers, and do you also foresee a market for like the next Facebook of quantum computers? Or
Yeah. So quantum computers, people need to kind of get their expectations wired up properly on them, right? Because we have 100 qubits maybe, right? We have a bunch of companies working on 100 qubit devices, and there's no papers on it yet. If you think about when Intel went from a couple hundred, well, in 71, Intel had a processor with 4,000 transistors. It took them about 30 years to get to 1 million transistors, okay? Current quantum computers are tiny, and while in principle they're more powerful, practically they're not more powerful in the sense of the kinds of problems that we can actually, that we do big machines with, simulations, AI, massive data analysis. Quantum machines will not be good at that for a long time, if ever. What they're going to be good at is quantum simulations, okay? So a quantum simulation would be something like modeling the electronic structure of an atom. You might say, well, what good is that? I'd say, well, let's say if I'm trying to model binding of a drug, okay, it might be useful for that. It might be useful for me doing certain kinds of experiments, where I'm going to do some kind of, say, atomic or molecular orbital experiments in physics, and I want to simulate a system with a lot of electrons, okay? Now, why am I saying it this way? And maybe you're not physicists and you don't get this. The point is that a quantum computer is a quantum system, and the thing that is going to be best at simulating is other quantum systems. And the things that are quantum systems are like the electrons in an atom, right? Or the relationship of atoms. So that's what quantum computers are going to be good for. They may eventually be able to solve certain kinds of optimization problems. Okay, it might be useful in industry, right? But there's not going to be a Facebook of quantum computing anytime soon. They're not going to balance your checkbook. They're not going to read your email on a quantum computer. You're not going to have a quantum computer in your phone, right? They're going to be, specialized devices that people tinker with for a long time and then eventually find some set of applications for. Now, that's quantum computing. You're going to see a lot more happening in quantum sensing. Okay, so quantum sensing is the ability for us to build incredibly precise sensors that can measure single photons or can measure single phonons, vibrations and heat and so forth, and capture that information and keep it in a quantum state and process it in a quantum state. And this could happen in communications, it can happen in security, it can happen in all kinds of scanners, right? You might be able to use it in biological or medical imaging, okay? So these are not going to be applications that, are going to affect you directly for a long time. It's critically important, though, because it's clearly possible for these things to exist. And if we can get them to work in the long game, right, in the 20, 30, 50-year game, they will completely change what's possible. But in the short term, they're mostly physics experiments. And so invest accordingly. Right.
I said final question, but we have one more coming up. Yeah, who are you? Where are you from?
I'm Javed. I'm from NTNU, Norway. Actually, I'm talking about this blockchain hype and cryptocurrencies. If there are quantum computers in that situation existing, the cryptocurrency systems will be affected or not?
Can you give a brief answer? Is it possible?
So I don't believe in blockchain, number one, and though I haven't thought about why you'd use a quantum computer to hack it, but blockchain, in a slightly less flippant version, blockchain involves reading a lot of data and computing a function on that data. Quantum computers are bad at reading a lot of data, okay? Think of it, quantum computers can't read data to first order. Every time you have to load data into a quantum computer, you're burning a quantum gate cycle. And right now, they can only stay coherent for a relatively short amount of time. You can use that to compute, or you can use it to read data in. And the amount of data you'd have to read in to actually do a blockchain calculation is beyond what a reasonable quantum coherency time is for a quantum computer. So in the near term, they're not going to have anything to do with breaking blockchain.
Thank you so much. Rick Stevens.
Thank you.